In today's lecture, we will move on to a new topic, and that is air duct design. By now we are familiar with the components of an all-air system, and on the air side of an all-air system we have the ducting, that is both for supply and return air. Then we have air filters, dampers, fans, etc. The function of the duct is twofold. One is to supply the correct amount of air to each of the zones, and the other is also to supply it at a given pressure. In addition, the noise levels are also to be taken into account, because when the air moves through ducts there is noise that is generated, and we have to ensure that the noise levels that are then transmitted to the conditioned space are within acceptable limits. Typically for a ducting system, the pressure loss is around 0.65 to 5 pascals per meter, and it will also vary whether we are talking about the main duct or the branches. We will look at that later on. If you look at the construction of duct, there are two principal sections of a ducting layout. One is the header or main duct, and the other are branch or runouts. So we have branches which take off from the header or the main duct, and then they are connected to the diffusers in the respective spaces in the zone. The shape of the ducts that are used, there are three principal shapes, of which two are the most commonly used, that is round and rectangular. The round ducts in general have certain advantages over rectangular ducts. That is, for a given pressure drop you will have a smaller cross-sectional area and a surface area for a round duct, and it has better rigidity and strength, but at the same time it requires more clear height for installation. So that is also something that we have to at times take into consideration, that there is a restriction on the room that is available through which the ducts are routed, and maybe a round duct in that case may have to be replaced by a rectangular duct, which you can see can be reduced in height if there is a requirement, that is the height that is available is relatively small. When we are using a rectangular duct, we will try to keep the aspect ratio, that is this ratio A:B, as close to 1:1. When you do so, you will see that it reduces the pressure drop and the surface area of the sheet metal that is used to construct the duct. And we can increase the aspect ratio. Probably 3:1 is fairly acceptable. We can go beyond that, but if we go to a value like 7 or 8:1, then it becomes prohibitive in terms of the very high pressure drop that you will experience with that sort of an aspect ratio. When we say that in general round ducts are preferable to rectangular ducts, they have a smaller surface area, that also translates into less material cost. So that is, they are going to be also less heavy, and we need hangers etc. to support the ducts, so we will require relatively hangers which are not that strong, in that sense that for rectangular duct we will need heavy hangers also. The other thing is that because the surface area for a round duct is less, the heat loss from the surface will also be reduced, and if you are insulating the duct, the insulation cost also goes down. So overall, if you have the option, we will go for round ducts. We also have ducts which are flat, oval, and in some cases we can also use flexible ducts, because with round ducts or rectangular or flat oval ducts, when you route the ducts through various portions of the building, you will need various fittings to turn them around at corners, etc. So there could be some places where it might be better to use a flexible duct, where rigid ducts may not be the right choice, but generally we'll prefer to have round or rectangular or flat oval ducts. A critical part of a duct design exercise is to evaluate the total pressure loss through a ducting system, and the total pressure loss has two components: the frictional losses in the straight parts of the ducts and the dynamic losses, which are the losses that occurred when the air passes through various fittings, that means elbows or T's or such other fittings in the ducting system. And to calculate the frictional loss in a duct, we have a duct friction chart that I will bring up on the screen, and we can use this chart to calculate the friction loss through a straight length of a duct. I will come to this chart shortly and show you how we use this chart. Okay, so you can see that we have the air quantity over here and the friction pressure loss. So you have the air quantity in liters per second, and you have the friction loss in pascals per meter. So this is the pressure drop per unit length. So if you know the length of a given straight section of a duct, you just multiply this value by the length of the duct to get the total pressure drop. The next thing, of course, is to look at the dynamic losses, and the dynamic losses are calculated by this formula, that is delta P is equal to KL into rho V square by 2. Half rho V square is the dynamic pressure, and it is multiplied by the loss coefficient to give us the dynamic or the minor loss in fittings such as enlargements, contractions, elbows, etc. And the loss coefficients are provided by the manufacturers. In fact, there is an ASHRAE database which will provide you with loss coefficients for over 200 different types of fittings which are used in HVAC duct systems. Okay. If you look at the friction chart, you will see that the friction chart, I will again bring it up later on, but if you look at that chart, you will see that it gives us also the diameters and velocities in the duct system. Because we have the diameters over there, it means that chart is for a circular duct. But we can also use the friction chart to find out the pressure drop for rectangular ducts. The way to do it is that we first find out an equivalent diameter given by this formula, knowing the rectangular duct dimensions, and we will use the volume flow rate, and using these two parameters we will find out the pressure drop per unit length for a rectangular duct. One word of caution, do not use D equivalent and the velocity to find out the pressure drop for rectangular ducts. If you are using D equivalent, then use the flow rate only for rectangular ducts. With circular ducts, we have a choice that we can use either the velocity and volume flow rate to find out the pressure drop per unit length. We can also find out the volume flow rate by using the diameter and volume flow rate. So this is a restriction that you have to keep in mind. I will now go to the friction chart, and then we'll look at how do we actually use it. Now if you look at the friction chart, on the horizontal axis we have the air quantity, and it is in liters per second. So if you are given the volume flow rate in cubic meters per second, make sure you convert it into liters per second. And remember, the pressure drop is given in pascals per meter. So we calculate the total pressure drop by multiplying the value that we read of the table by multiplying it with the length. Now we also have the duct diameter over here. You can see the duct diameters are increasing in this direction, and the values are given over here. So for example, this value that I've shown by this line over here, it is between 800 and 1000 millimeters, so it is around 900 millimeters. So the diameters are given in millimeters. Similarly, if you look at the velocities are given in meters per second. So over here we have the velocities, and the velocities are increasing in this direction. And again, the line that I have drawn over here is showing the velocity is between 35 and 30 meters per second, so it is 32.5 meters per second. So you have the various velocities over here, starting from 1.2 etc. Then we go on to higher values in this direction, and the diameters are increasing in this direction. And how do we read the value? For example, we are given that in a duct we have a volume flow rate of 3 cubic meters per second, and the velocity in the duct is 5 meters per second. So we have this vertical line. We have converted the 3 cubic meters per second into liters per second, so that is 3000 liters per second. So you draw a vertical line, and then you draw a line which has a velocity of 5 meters per second. Where they intersect, then you draw a horizontal line that you can see over here, and then read the value from the scale for the friction loss, and the value over here we can see is around 0.275 pascals per meter. If the velocity that you are given is, let's say, 5.5 meters per second, then you will have to draw a line yourself like this, and then again read of the value of the pressure drop from the scale on the vertical axis. So that is how you can calculate the friction loss for a circular duct. If you want to use a rectangular duct, you will first have to convert it into an equivalent diameter, then use that value on the chart. For example, if we have a rectangular duct which is 1 meter long, and the two sides are 660 millimeter and 265 millimeter, then if you calculate the equivalent diameter will come out to be 446 millimeter. What it means is that if I am going to replace that rectangular duct with a circular duct such that the pressure drop remains the same, what should be the size of that circular duct, and you can see that the circular equivalent diameter will come out to be 446 mm. So a 446 mm circular duct will give you the same pressure drop as a rectangular duct which has dimensions of 660 mm and 265 mm. So we are keeping the pressure drop the same and then finding out D equivalent. But again, keep in mind we will only use D equivalent with the volume flow rate. So we will come back to the lecture, and this is the way we will calculate the total pressure drop. First you will find out the friction losses, then you will find out the dynamic losses, add them together, you will get the total pressure drop for the particular duct system that you are analyzing or designing. We now move on to the classification of duct systems, and the classification can be done on two basis. One is the velocity classification and the other is pressure classification. The velocity classification again has three principal categories, that is high, medium and low velocity systems. The values of the velocities in a high velocity system I have shown. That's in the main duct we will have a higher velocities in general, and in the branches we also have lower velocities. So for a high velocity system, the main duct velocity could be typically around 20 meters per second, whereas the branched velocities are around 15 meters per second. Similarly, for medium velocity systems, the velocity ranges between 10 and 15 meters per second. Low velocity systems, we have even lower velocities. And then if you have ducts in areas where you require very low noise levels, you might go to velocities as low as 3 to 4 meters per second, because the noise levels are related to also the velocity of the air in the ducts. So higher velocities lead to higher noise levels. Then the pressure classification, also we have the three categories, that is high pressure systems, low pressure systems and medium pressure systems. Again, as a broad guideline, duct systems which are classified as low pressure, the pressure is about 1000 pascals, and this is, we are talking about the gauge pressure in the ducts. And the medium pressure systems, the gauge pressure ranges from 1000 to 1500 pascal, and high pressure 1500 to 3000 pascals. If you look at the general features of a duct system, you will see that the primary or the main ducts are generally medium pressure, and the secondary or the duct system, that is the branches or runouts etc., are low pressure classification. High pressures are not that much encountered, but if there is a need for that, you will go for that, because higher pressure means we need to have thicker ducts which are consume more materials, which are heavy, and they tend to become quite expensive. And generally the duct strength, deflection and leakage are functions of pressure, while noise, vibration and friction loss are strongly dependent on the velocities inside the ducts. We will go to the duct design methods and just go through the process that we have for a particular type of a method, and then later on we will go through an example in which we will apply two of these methods for designing a duct. If you look at a simple duct layout that is shown over here, you have the fan, and from the fan you have the main branch, main duct, and from the main duct you can see the branches which are taking the air to the various spaces through the outlets which have been numbered 1, 2, 3, 4, 5, and various segments of the duct system have been labeled by using letters. So there is no hard and fast rule. You can also use numbers for the segments, or you can number the nodes. The only thing is important is that we are able to identify those segments and the outlets. So the first thing that we will need to have is the duct's layout, and the duct layout we will of course depend on that from the building plan, because we will have to route the ducts once we have the building plan, and we will also need to know if there are any obstacles in the routes, so we have to route the ducts around those. Okay. So we have the main duct, and from the main duct you have seen there are various branches going into the various parts of the conditioned space. When we calculate the pressure drop, the way to do it is that we calculate the pressure drop from the fan to each of the outlets. Now if we start from one outlet, and I will just take one of the outlets. Let's say if I go from over here and I go to outlet number 1. So that is called a run. So if we talk about run number 1, run number 1 consists of segments A and B, and in this run we have the straight part of the duct, and there might also be dynamic losses due to any fittings. For example, if there is a T over here, or there is a bend somewhere, or an elbow, that will lead to minor losses or dynamic losses. Similarly, at the exit there could be, or there will be, dynamic losses. Even at the inlet into the duct there are going to be dynamic losses. So we have to calculate the pressure drop through each of the runs. If I go from over here to another outlet, let's say I am going if I go to outlet number 5, so that run number 5 will consist of segments A, C, G and I, and any other fittings that we encounter in this run. So we will have to calculate the pressure drop separately for all the runs. Once we have done that, we will be able to identify the run with the maximum pressure drop, and that run is known as the index run. And it is important to know the index run because the fan selection will be based on the index run. The pressure drop, maximum pressure drop that you encounter, must be overcome by the pressure that is developed by the fan. Okay. So we have the load for the conditioned space. According to the load, we will know how much is the supply rate of the air required in that conditioned space, so we will know the volume flow rate. What we will also have, as I mentioned earlier, from the building layout, the location of the supply fan and the route or the layout of the duct runs is also known to us. What we will be asked to do when we say we are going to design a duct is that we will select suitable dimensions of the duct. If it's a circular duct, we will find out the diameter for the main duct as well as the branches. Then we will of course need to find out the pressure drop in each of the runs, identify the index run, and then we select a fan that will be used to drive the air through the ducting system to the various outlets. When we look at a large project, the duct layouts are quite complex, and nowadays we quite commonly use softwares for designing the duct systems. However, for simpler layouts like the one that we had looked at, and those are the types of layouts that we will work with in this course, we can use manual methods. For example, the velocity method, equal friction method, and there is a third method called static regain method, which I wouldn't call suitable for manual work because it is an iterative method. So we will restrict ourselves to the velocity method and the equal friction method.